In the fourth question, we are using the attend dataset. In this question, there are 5 parts. In the first part, it says obtain the minimum, maximum, and average values for the variables attendance rate, prior GPA, and ACT score. In the second part, attendance rate is being explained by prior GPA and ACT score. In the third part, it says to discuss the estimated slope coefficients. In the fourth part, it says what is the predicted attendance rate if prior GPA is equal to 3.65 and ACT score is 20. And in the fifth part, it says if a student has a prior GPA of 3.1 and ACT score of 21, and student B has a prior GPA of 2.1 and ACT score of 26, then what is the predicted difference in their attendance rates? So now first load the dataset. Attend equals to data in the bracket attend. Then display the first few rows of the dataset by typing print in the bracket attend.head. So these are the column names in this dataset. Now first part, compute minimum, maximum, and mean for attendance rate, prior GPA, and ACT. So we can do all of these functions in just one command by typing stats equal to, select the dataset name attend, and in the bracket, square bracket, type the column names for which we want this summary statistics, and then type dot agg, that is aggregate, and we want minimum, maximum, and mean, average, that is average value for these columns, and then type print in the bracket stats. So you can see here are summary statistics for these 3 variables. Okay, so minimum value of attendance rate is 6.25 for and maximum is 100 and average is 81.7. For prior GPA, minimum value is 0.85, maximum is 3.93, and average is 2.58. For ACT score, minimum is 13, maximum is 32, and average is 22.51. In the second part, it says to estimate the regression model where attendance rate is being explained by prior GPA and ACT score. To create a model equals to smf.ols. In the formula, type attendance rate tilde prior GPA and ACT score. So, and the dataset name is attend.fit function. Extract the estimated coefficients by typing beta 0, beta 1, beta 2 equals to model.params. So estimated equation is attendance rate equals to 75.7, that is, this is the intercept, plus 17.26 on prior GPA. So the coefficient on prior GPA is 17.26 and the coefficient on ACT score is minus 1.71. So what is the interpretation of intercept? The intercept 75.7 represents the predicted attendance rate when prior GPA and ACT are both 0, which is unrealistic in practice. Now we have to interpret the slope coefficients. So slope coefficient on prior GPA 17.26, it means that a 1 point increase in GPA is associated with a 17.26 percentage point increase in attendance. And the coefficient on ACT, that is minus 1.71, means that a 1 point increase in ACT score is associated with a minus 1.72 percentage point decrease in attendance. Okay, that word here should be decrease. So I will change it right now because the coefficient is negative. Now in the fourth part, it says predict attendance rate for prior GPA equals to 3.65 and ACT 20. So create a variable prior GPA underscore test equal to 3.65 and ACT underscore test equal to 20. So, and now create a variable predicted attendance rate equals to beta 0 plus beta 1 into this value prior GPA plus beta 2 into this value ACT underscore test. So now what is the answer? So predicted attendance rate for prior GPA 3.65 and ACT 20 is 104.37%. Okay, that is equal to 100%. Now it says to check whether there is a value in the dataset where prior GPA is equal to 3.65 and ACT is equal to 20. So create a variable matching underscore students equal to dataset name. In the square bracket, select the column prior GPA equals to prior GPA test and attend, and then again type the dataset name, select the ACT column equals to this value. So the answer is there are no exact matches in the dataset for these values. Now in the fifth part, it says predicted difference in attendance rates between student A and B. Student A has a prior GPA and ACT score of 3.1 and 221, and student B has a prior GPA of 2.1 and ACT score of 26. So predicted difference is calculated by multiplying beta 1 into prior GPA plus beta 2 into ACT score of student A minus beta 1 multiplied by prior GPA of student B plus beta 2 into multiplied by ACT score of student B. So predicted difference in attendance rates between student A and student B is 25.84 percentage points. So we are done with this question. Let's move on to the next question. So in this question, we are using the dataset wage 1, and in this dataset, we are being asked to confirm the partialing out interpretation of the OLS estimates by explicitly doing the partialing out for example 3.2. So this is the example 3.2 mentioned in the book. So it says this first requires regressing education on experience and tenure and saving the residuals, then regress log wage on residual from equation 1, and then we have to compare the coefficient on residual from the equation 1 with the coefficient on education in the regression of log wage. So basically what we are doing, the objective of this question is that to show that the coefficient on education and the multiple regression of log wage on education, experience and tenure is equal to the coefficient on the residual from regressing education on experience and tenure when that residual is used to predict log wage. So let's see the steps. First, load the dataset, create the data frame wage equals to wo.data wage 1, and then display the first few rows of the dataset by typing the head command. So these are the columns in the dataset. Now first we will estimate the full model where log wage is being explained by education, experience and tenure. To create a model underscore full equals to smf.ols in the bracket formula L wage tilde education plus experience plus tenure, dataset name is wage and dot fit. So first look at the coefficient of education. It is 0.09. Now we will save this parameter coefficient of education. Type beta 1 equals to model name model underscore full dot params and then type the column name education. Now we will regress education on experience and tenure. So create a model underscore partial equals to smf.ols in the formula type education tilde experience and tenure, dataset name is wage, then dot fit function, and then we have to save the residual from this equation. Okay, we have to save the residuals from this equation. We will later on use residual to predict log wage. So create a new column by the name of R1 wage in the square bracket R1 equals to model underscore partial dot resid. So residuals are saved in this column R1. Now we will regress log wage on this residual. So create a new model underscore residual equals to smf.ols and the formula L wage tilde R1 and the dataset name is wage dot fit. So this is the result of regressing log wage on residuals, and look at this coefficient. The coefficient on residuals is 0.009. Okay, now why did this happen? Basically residual is variation in education that is not explained by experience and tenure from this equation. Okay, so residual is variation in education that is not explained by experience and tenure. So this isolates the part of education that is orthogonal or uncorrelated to the controls. And now what is the interpretation of this coefficient? R1, the coefficient on R1, we can also say, let's suppose it is delta 1. So delta-1 now measures the effect of the component of education that was orthogonal to experience and tenure on log wage. Okay, it measures the effect of education that was not explained by experience and tenure on log wage. Therefore, this is important in causal inference. Okay, so this exercise shows that multiple regression controls for other variables. Basically, the purpose of this question was to show that multiple regression controls for the effect of other variables. That's why the coefficient on this residual is equal to the coefficient of education in the full model. Okay, so these coefficients are nearly identical, and that's why it confirms the partialing out interpretation. We are done with this question. Let's move on to the next question. So in the sixth question, we are using the dataset wage 2, and in this question, we are showing the omitted variable bias. The objective of this question is to understand how omitting a relevant variable from a regression affects the estimated coefficient on another variable when explaining the y variable, or you can say explained variable. So now let's follow the steps of this question. First, load the dataset wage equals to woo.data in the bracket wage 2. Display the first few rows of the dataset by typing head command, and these are the columns in the dataset. Now first we have to run simple regression of IQ on education. That is, IQ is being explained by education. Now extract the coefficient from this equation by typing d1, that is delta 1 equals to model underscore IQ dot params in the bracket type education. Now we will run log wage on education. That is, log wage is being explained by education. So first we have to create a column by the name of log underscore wage equals to np.log. In the round bracket type the dataset name, and in the square bracket type the column name wage. Now create a model underscore log underscore wage equals to smf.ols. In the formula type log wage tilde educ, that is education, and the dataset name is wage. Then dot fit function. Extract the coefficient from this equation by typing beta 1 equals to model underscore log underscore wage dot params and this column name education. So from the first equation, when we ran IQ on education, the coefficient delta 1 is 3.53. Now from the second equation, where we are running log wage on education, the coefficient beta 1 is 0.05. Now we will run the multiple regression of log wage on education and IQ. Create a model name by the model underscore multi equals to smf.ols. In the formula type log wage tilde education plus IQ. In the dataset name type wage dot fit. Extract the coefficients on both the variables by typing beta 1 underscore hat equals to select this model name dot params and then education column. Then type beta 2 hat, type the model's name, and then in the square bracket type the IQ column. So the slope coefficient on education is 0.03 and slope coefficient on IQ is 0.005. Now we have to verify that beta 1, calculated beta 1 is equals to beta 1 hat plus beta 2 hat multiplied by delta 1. So create a variable calculated underscore beta 1 equals to beta 1 hat plus beta 2 hat into the delta 1 from the model from the first equation, and the beta 1 is the simple regression of log wage on education. So what is the result? The result is 0.0598, that is similar to the slope coefficient on IQ. So basically it shows that if you omit a relevant variable from the equation, it will create a biasness in your equation. It will introduce biasness in your results because IQ affects the dependent variable log wage, and is correlated with an included regressor, that is education. Therefore, it will introduce omitted variable bias. So the objective of this question was just to show that you have to include all the relevant variables that may impact the explained or y variable. Okay, so we are done with this question. Let's move on to the next question. So in the seventh question, we are using the dataset MEEP93. In the first part, we have to estimate the model where math 10 is being explained by logarithm of expenditure and lunch program. In the second part, it says, what do you make of the intercept you estimated in part first? In particular, does it make sense to set the two explanatory variables to 0? The third part, it says, run the simple regression of math 10 on log expend and compare the slope coefficient with the estimate obtained in part first. In the fourth part, it says, find the correlation between log expend and lunch program. And in the fifth part, it says, use part fourth to explain your findings in part 3. So first, load the dataset MEEP equals to wo.data in the bracket MEEP93. Print MEEP.head to display the first few rows of the dataset. Now let's estimate a multiple regression where math 10 is being explained by logarithm of expenditure plus lunch program. Create a model 1 equals to smm.ols and the formula math 10 tilde l expend plus lunch program. In the dataset name is MEEP.fit function. So these are the results from the regression analysis. Now extract the intercept for its interpretation. Beta 0 equals to model 1.parens in the square bracket type intercept. Estimated intercept is minus 20.36. So setting log expend equals to 0 and lunch program equals to 0 doesn't make sense practically because the intercept is a negative value, which is unrealistic. In the third part, we are estimating a simple regression of math 10 on log expend. So create a model 2 equals to smf.ols formula math 10 tilde l expend, and the dataset name is MEEP and .fit function. These are the simple regression results. Now we have to compare the result from multiple regression and simple regression. So extract the coefficient first from multiple regression, beta 1 underscore mult equals to model 1.parens l expend, and then beta 1 underscore simple equals to model 2.parens in the column in the type in the square bracket the column name l expend. So estimated spending effect in multiple regression is 6.22 and estimated spending effect in simple regression is 11.16. So in the simple regression, the coefficient on L expend is more, which is maybe due to omitted variable bias because we have not included other relevant variables that might explain the score on mathematics. Now let's calculate correlation between L expend and lunch program. Create a variable correlation equals to MEEP, and then in the bracket select the column name L expend and lunch program dot CORR function core function dot ILOC in the square bracket 0,1. The correlation between log expend and lunch program is minus 0.19. So the negative correlation between these two variables suggests that higher school expenditures are associated with fewer students in lunch program. So this explains why omitting lunch program inflates the estimated effect of spending on math scores in simple regression. If there would have been a positive correlation, then we could have said that omitting lunch program may cause an omitted variable bias in the spending coefficient. Okay, so we are done with this question. Let's move on to the next question. Thanks for watching. If you found this helpful, don't forget to like the video and subscribe to the channel for more content like this. See you in the next one.